network covalent atomic solids. So carbon is like the champion here. Elemental carbon exists in several different forms called allotropes. So graphite is one, and that's what's in the pencil you might be using. And in graphite, the carbon atoms are covalently bonded to each other in two-dimensional sheets. And the individual sheets are held together by intermolecular forces, just dispersion forces. As a result, the connection between adjacent sheets is very weak, and so they can slide, right? And so that's what makes graphite slippery. And as you pull your pencil across the paper, layers of it slide off and stick on the paper. Graphite's a good electrical conductor because it's got this extended pi bonding network, and that's, we're talking about the molecular orbital business. And so it can actually conduct electricity even though it's not a metal. So graphite has a density of 2.2 grams per cubic centimeter. Under high pressure, the graphite can rearrange and have a density of 3.5 grams per cubic centimeter. And this allotrope is called a diamond. And, a diamond looks a lot different than graphite, right? Graphite is soft and slippery and black, and diamonds are very hard and beautiful, right? What's the difference? Well, here, these carbon atoms are bonded to each other in 3 dimensions instead of just 2. So we've got covalent bonds all over the place, and that's what makes it very hard. Graphite is soft because you can always slip those layers apart from each other. But here you have to break a lot of covalent bonds in order to cut a diamond. So diamonds, are found naturally. They come from graphite, and they can be synthesized. It takes pressures of like 50,000 atmospheres and to high temperatures, 1,600 degrees, if you want to speed up that process. It was kind of expensive. If we look at the unit cell structure of carbon in the diamond, so this was that zinc blend structure we were looking at, and this is graphite. And what graphite is doing is each carbon atom is covalently bonded to 4 other carbon atoms that are in these tetrahedral holes. So this one would be bonded to 4 different atoms. And so that's like this guy over here. And so overall, there's a structure that is a face-centered unit cell with, again, atoms in the tetrahedral holes. It's really high melting point, very hard. Conducts heat, but not electricity. Okay, high pressure favors the formation of diamond from graphite. What can you conclude about the relative densities of these 2 substances? Diamond is denser than graphite is denser than diamond, or we can't, we need more information. So if you take graphite and you put a lot of pressure on it, you make diamonds. Is the diamond more compact or more spread out than the graphite? It's more compact because it's got squished together. So is its density going to be bigger? Yeah. So the density of a diamond is greater than the density of graphite. Other forms of carbon, back in the 1980s, they discovered something called Buckminster fullerene. And this is shaped like a soccer ball. And so we've got these clusters of atoms forming these little balls, and then those are held together. So Buckminster fullerene has 60 atoms. There are other ones, they're also called buckyballs. They can be anywhere from 36 to over 100 carbon atoms in a cluster. And so researchers have figured out how to do some really cool things with this. So they can make carbon nanotubes. So this is a little bit like chicken wire, right? Let's look at this one, it's flat. This is a ribbon. So each of these hexagons is 6 carbon atoms that are bonded together. And so you can make a long ribbon of that. It's going to conduct electricity. Or if this is rolled into a tube, you can have a single-walled nanotube, or you can have one that has a bunch of nanotubes inside of it. And then this is the graphene sheet they were talking about in the first part of this book. So, you know, when you hear about like a bike that's really lightweight because it has a graphite core, or graphite golf clubs, like, well, pencil lead, how is that good? Okay, it's not graphite, it's this kind of carbon. It's nanotubes and carbon fibers, and they're extremely strong. The nanotubes are 100 times stronger than steel and 1/16 as dense. So really awesome for lightweight applications. You can use bundles of nanotubes to form really tiny wires. Then there's other covalent atomic solids, silicates, and these are silicon and oxygen that are bonded together. And there's not individual molecules here. They're all bonded together. So that makes it different than a molecular compound. And silicates, there's different varieties of them, but that's what sand is made up of. And so about 90% of the Earth's crust is made up of things like this, silicon and oxygen network covalent solids.